The first essential question we should ask is, why are we here? What are blockchains, or more broadly, what are distributed ledgers? What is consensus? Why is this important? And what are the design considerations at play as we try to construct these systems? What aims are we trying to satisfy? Who are the stakeholders in the network? And how are the choices we make formulated to satisfy those aims? First, what is a distributed ledger? A distributed ledger is simply a way of splitting some state machine and replicating it across multiple computers. A state machine is an abstract model with some state, let's call it S, defining some set of data, some transaction type, call it T, defining a way in which that data can change, and some update function U, which takes an old state, a transaction, and returns a new state, where the transaction updates the state, perhaps changing a balance or altering some property of an object. This abstract model is very flexible. It can model any state, which can change in a deterministic way according to which transactions are applied. It can be used to model a currency, or financial products, derivatives, bonds, options, stocks. It can be used for identity, or record keeping in a governmental context, or maybe a healthcare context. It can be used to model virtual worlds. Any game you've played has a state machine, perhaps including some randomness, but still with its basic form. A distributed ledger takes this kind of a state machine and replicates it. Why would we want this? Mostly at the moment we have centralized ledgers, where the data, called the state, and the rule set, U, are controlled by one entity. That entity might be a bank, might be a for-profit company, but necessarily, if the ledger is centralized, it's a trusted party, because the entity controls both the data and the rule set. So in order to know, if you're a consumer or someone who's utilizing the state machine, you must trust the company to both keep the data, store it correctly, and to correctly apply U. Often they claim that U is some particular update set, so your bank will claim that you really send someone money when you press send, or when you call someone on the phone, and then if someone sends you money, you'll get it in your bank balance, but you must trust that bank or that central party to correctly apply the update function each time someone sends a transaction. However, these ledgers are common goods, or commonwealths. We want it to be the case that many different people can utilize such a distributed ledger because it provides net benefit to the economy of people using it. And it's ideal if that doesn't require trusting the central company or the central party, because the central party's incentives are not necessarily aligned with those of everyone using the ledger. So we might try to distribute the ledger, to make it the case that anyone could read and write S, could apply these transactions, and could verify that the function U was applied correctly to each state in each transaction. This introduces lots of complications, hence the field of blockchain development, but it provides some pretty core benefits, which one might have reason to think are worthwhile or worth a lot of research. It makes it the case that since anyone can generally read or write state and apply these transactions, you can innovate, you can build upon these state machines, compose them perhaps in ways that don't require permission. So you can write some kind of software on top of the state machine, maybe a different state machine, or maybe an interface to another kind of software. And that software can generate transactions or can read existing transactions. You don't need to work with a party who's controlling the ledger and controlling the rule set and convince them to change the rule set or to allow you to modify the ledger in certain ways. You can just do it. Distributing a ledger also provides a very high degree of transparency and auditability because of the way in which you must distribute a ledger. It is the case that everyone must be able to verify that the update function U was executed correctly for each transaction in each state. So you don't need to worry that a central party with misaligned incentives might change things when it benefits them. If we do this naively, if we take a ledger and replicate it across many different computers or even many different clipboards in the abstract model, we run into some problems. One of the first key problems is called the double spend problem. So let's say we replicate this ledger, so everyone keeps a copy of the state and everyone sends each other all the transactions. Just writes letters or sends computer digital messages over the internet saying maybe for a currency who sent what to whom. So I send a transaction to Bob. I'm Alice. I send a transaction to Bob, 5 units of currency, and I send the data this transaction has, maybe including some kind of authentication, a signature, to everyone else in the network. But what if they don't see it at the same time? What if someone else, or maybe me, being malicious, sends 2 conflicting transactions? I spend the same money twice, or I attempt to do so. I sign one transaction that sends my 5 units of currency to Bob, and another transaction that sends them to David. And I broadcast these transactions to different parts of the network. Then the network has to, if we want it to come to consensus, if we want this currency to be functional as a currency, one of the essential properties of a currency is that it cannot be double spent, otherwise it's not very useful. You want it to be the case that someone can send 5 units of currency only once, and that those 5 units of currency are conserved, or that the total balance of the currency is conserved. So we need some way for the network as a whole, for all of the participants running this ledger, to choose between these 2 histories. They've seen 2 conflicting transactions. Maybe they've, even if I sent them originally to 2 separate halves of the network, they've gossiped them between each other. That's pretty easy. But they need a way to choose which one to apply, because only one can be applied to the state in a consistent fashion that results in the preservation of the rules we want to preserve. And generally, we'll say that they need some function f. That function f needs to take 2 histories, 2 alternative but conflicting histories, and choose one. And we need everyone who is running this ledger to use the same function. If they use the same function, then we can be confident that if 2 people in totally different parts of the network are choosing between 2 histories, as long as they see the same set of histories to choose between, they will choose the same history, and so we will have consensus on, in this case, who has which amounts of currency. This relates back to a problem that is relatively old in the academic literature, at least old relative to computing, the Byzantine Generals Problem. In the Byzantine Generals Problem, a group of generals command the Byzantine army. The Byzantine army is a medieval army encircling a city and intending to either attack it or retreat. Each of these generals has to choose independently whether to attack or retreat with their subset of the army's forces. And they can send messages to other generals to coordinate. It's essential that they coordinate because if they take different actions at the same time, catastrophe will occur. If some attack and some retreat, the attack will be a failure because they didn't have enough troops, or the retreat will be a rout because the army within the city perhaps comes out and encircles their retreating forces. But these messages that they can send to other generals in order to coordinate may be arbitrarily delayed or even possibly forged. So some messenger from the city in the metaphor could capture any messenger between these 2 generals and kill them, or could forge a message and try to convince one of the other generals that the first general had said something that in fact they hadn't said. So using this model, which maps pretty cleanly onto the double spend problem, his messages getting delayed or sent to different parts of the network at different times, but we can authenticate messages. We have some way to know that a general did or did not send a particular message, and everyone else in the network, all the other generals who are receiving these messages, can check whether a message is valid or not. So let's say we have H honest generals and D dishonest generals. We'd like to figure out what these values can be and still come to consensus. So honest generals are defined as following the rules of the protocol. So in particular, they send only the same message to everyone else. If I'm an honest general, I choose whether I'm going to vote to attack or to retreat, and then I send that vote to every other general via messenger, and I send them all the same vote. Dishonest generals, Byzantine generals, are going to behave in the way which puts consensus most at risk. Maybe they're working for they're double agents, secretly working for the opposing army. And these dishonest generals are going to send different messages to different generals. So they're going to assign 2 votes, 1 vote to attack and 1 vote to retreat, and they're going to send these votes to different generals, trying to split up the network and get different generals to make different decisions. All generals wait for messages from all the other generals before deciding what to do. Messages keep getting delayed, we can never make progress. But we know that if enough messages get to the generals, we can make some progress. So if we have total number of generals or nodes n, which is of course just the sum of the honest and the dishonest, the worst case is that half the honest generals want to attack and half them want to retreat. So they've all cast their votes, and the dishonest generals have waited to hear these votes, and then they figure out what the optimal way they can attempt to partition the network of generals is. And that is to, of course, tell the first half of generals that the dishonest generals intend to attack, tell the second half that they intend to retreat. Then we have half the honest generals and all the dishonest generals from the perspective of the honest generals agreeing on attack, and half the honest generals and the dishonest generals from the perspective of the other half of the honest generals agreeing on retreat. So that means if we want to maintain safety, if we want it to be the case that we can never come to a separate decision, we'll just keep waiting, we must require a threshold of votes greater than half the honest generals plus all the dishonest generals. If you simplify this a bit, this translates to that over 2/3 of the nodes must be honest. This is the 2/3, 1/3 result in classical BFT theory. That if you want to safely come to consensus on a next step, or a next state, or the application of a transaction, which are all the same problem, you need at least 2/3 of nodes to be honest, and you must wait to receive 2/3 of votes before you can proceed. So, how do we turn this into a distributed ledger? Well, a first try would be to take the sort of simple, it needs to be a multi-round voting procedure. I glossed over some complexity, but take the BFT voting procedure and translate it onto a distributed ledger. So here we must presume that we have some identity primitive. Like I said, there's a way that we can authenticate messages from these generals. We can know, anyone else, any other general can know, that a particular general did or did not sign a message. And we can always ensure that no one can forge messages. Then we simply use the fork trace rule F, as we defined earlier, of whether or not a particular history, particular updated state, or sequence of such updates has been signed by 2/3 of the validators, the generals in this problem. We start calling them validators in a blockchain context. This works. It allows us to safely maintain consensus, but it has some disadvantages. One disadvantage is that we assume, for safety, that 2/3 of the generals are honest, and we assume that not only at the current time, but we assume it over all time. So if, for example, some old generals had been honest when they participated in consensus, but they could now sign a different history. Nothing prevents them from signing multiple votes with the same key. And then if new participants join the network, participants who hadn't previously heard about the first sequence of votes, they won't safely be able to distinguish between these two histories. They will just see two different possible sequences of transactions, sort of forking at some point in the past, and there will be no way for this fork choice rule to safely distinguish because multiple histories have been signed by 2/3 of validators. Another problem with proof of authority is that it's fairly easily targetable. There are different ways to sort of elect which validators are going to propose the next step, the next transaction, the next block, but regardless of which way you do it, it is generally true that because these validators must be so clearly identified, it is fairly easy to assassinate them or to DOS them, as is more likely, or the equivalent in a computer science context. So it's targetable. And then it's also static, because you must have this clean identity model. Maybe it's somewhat dynamic. Maybe you can add new identities. Old general sets can vote to approve a new identity. But it's still the case that a general set can become entrenched and maybe extract some rent for network users. So of course we go back to the fact that with a distributed ledger, we're trying to provide a commonwealth. We're trying to provide the common denominator solution for the network of people who want to utilize, usually for some kind of economic trade or some kind of peer-to-peer interaction, want to utilize this ledger. And we want it to be the case that they can't, or it's difficult for the validators of the network to overly control the rules or extract a lot of rent from the people who want to use the network. And if a set of proof of authority validators becomes entrenched, that might be likely to happen. So what are our design goals, returning to that aspect, in designing a consensus algorithm for our distributed ledger. One is that we want a dynamic validator set. We want it to be the case that validator set can change. Anyone can join if they want, and if they maybe have some requisite resource or some requisite ability to help the network. And we especially want it to be the case that bad actors can be removed. So we usually have some protocol rules. There are ways in which validators can behave which are in compliance with the protocol, and there are ways in which they can behave which are not in compliance with the protocol. Even worse, are Byzantine, actively put the safety or liveness of the protocol at risk. And as much as possible, if we can identify these actions and remove the bad actors, we would like the ability to do so. We also want validator sets to be as anonymous as possible, to minimize the degree of public identity which is required to validate, to participate in consensus, and to even minimize the degree of pseudonymous identity, maybe IP address, though we're always going to need some kind of cryptographic keys to authenticate messages, but that is pretty pseudonymous. So we want to minimize the degree to which these validators can be identified and politically lobbied or DOSed. So if we just remove identity, though, our consensus no longer works, because anyone can masquerade as another validator. Anyone can pretend to be multiple different validators. We no longer have the ability to authenticate messages between one one validator to another, and one dishonest node could fabricate any number of messages, can break consensus. So, of course, we could institute some kind of central party maintaining a ledger of identities, which could be kept private by that central party. But then that central party must be trusted, and you would easily end up with the same situation where they have complete leverage over the network because they control through this identity authentication consensus. So we want to avoid that. We need some kind of hybrid system where we have the minimal amount of identity required and that also allows for a dynamic validator set while avoiding central identity verification. Another factor to incorporate into the mix is what kind of threat model or security assumptions we would like our consensus algorithm to have. We want this to be minimal, so we want it to be the case that we reach consensus safely and optimally maintain liveness in the case of as few assumptions about the network as possible. And we can do a little better than assuming two-thirds honest, both at a point in time and over history. In particular, we can model network participants as rational actors, so as actors who will behave in their own best interest, usually in the immediate timescale, but sometimes over a longer timescale, is a weaker assumption. And it so happens that in designing these distributed ledgers, we have generally control over both the consensus algorithm and the state machine. So we can tweak properties of the state machine, maybe in order to punish bad actors, in order to reward good actors, and try to construct such incentives as mechanisms to ensure that rational actors do the right thing, behave more often than not in the best interest of the protocol. So a second try for our consensus algorithm would be proof of work. Proof of work uses a different kind of scarce identity. It doesn't use public identities. Instead, it uses work, verifiable computation. And in proof of work, it generally takes the form of an asymmetric hash function or an asymmetric oracle. This takes some time to compute, and it randomly generates output based on the input. Generally, for proof of work, it must be the case that it takes a long time to compute an input that satisfies a particular function on the output, maybe that the output has a certain number of leading zeros. But once such an input has been constructed, it is very cheap to verify that it satisfies the requisite property. So it takes a long time in Bitcoin, which is the classic example, to mine a block to find a header and a nonce that satisfy the conditions on the output of the hash function, but it's easy for anyone to verify that the block is valid once they have the input. This was originally invented not for distributed ledgers or blockchains, but with Hashcash to prevent email spam, to try to make it costly for companies to send a lot of nonsense email by requiring that they submit over the body of the email and some nonce, a hash function lower than some target, just like in Bitcoin. I don't think it worked with email because it was the case that companies which wanted to spend spam could just rent a lot of computing power. But it was a novel idea, and it turned out to be much more useful in the context of blockchains. Bitcoin and many subsequent inspired blockchains utilize proof of work, where each validator participating in the Nakamoto consensus, pioneered, of course, by Bitcoin. Each validator participating in network consensus must commit work, and they must commit it to one particular history. This works by utilizing as the input for the hash function h not only a randomness and nonce, but a commitment to a particular history, a Merkle root of a block, for example. And the output of this function h must be below a particular value. So then the asymmetric computation verification, as in the previous slide, works here. In this target value, which it must be below, can be changed. This is the difficulty in Bitcoin, which can be adjusted according to the actual amount of mining power in the network, which can be measured automatically. So the difficulty can be adjusted every so often in Bitcoin, every 2 weeks. Nakamoto consensus is deployed in practice in Bitcoin, which has been running more or less successfully for almost 10 years. And it does solve many of the key problems. It allows for a dynamic validator set, so anyone can join or leave as they wish, and it requires a minimal amount of identity, almost no identity at all, simply the input to a hash function which commits work to a particular history that satisfies a particular output target. However, it also has some problems. One problem is that Nakamoto consensus has some built-in speed limitations. Because of the fork choice rule used, the longest chain, or the chain with the most cumulative work, will be chosen by all the nodes in the network. If nodes in the network can't communicate fast enough, you'll end up with many forks. So if it's the case that different miners, very quickly find new blocks, but they're in different parts of the world, then new miners in their part of the world will start building on their blocks before maybe the other miners see their blocks. Then you end up with many-headed hydra of forks. So in order to combat this, basically you have to introduce artificial speed limitations, a minimum time between blocks, enforced by the difficulty adjustment algorithm, and that limits the speed at which your network can process transactions. If you have a minimum time between blocks, consensus is much safer because you can be fairly well assured that most of the other participants will have heard about a new block by the time that they can themselves mine one. Another disadvantage of Nakamoto consensus, as very clearly demonstrated by Bitcoin, is that it consumes too much energy, and worse, it consumes energy in proportion to the desired amount of network security, or some rough proportion. So the more energy which is put into calculating inputs to this hash function, and the higher the difficulty gets, possibly the more difficult it is for anyone to put consensus at risk, any individual actor. But this has a huge negative externality of doing all this work, consuming all this electricity, simply to secure the consensus algorithm. Another problem is that it requires approximate synchrony in order to demonstrably reach consensus. It must be the case that all of these validators, and indeed anyone watching the network, can communicate with each other within a bounded period of time, so they can hear about any new longest chains and choose the longest chain. In practice, this means that in order to accept transactions over a network in return for some external resource, in order to consider transactions confirmed and irreversible, you must pick some number of confirmations after which you consider transactions to be finalized. Often in Bitcoin, this is 6, which is somewhat arbitrary. The higher number of confirmations you wait for, of course, the more confident you can be that a transaction will not be reversed, or reversed is a bit incorrect nomenclature-wise, but a transaction will not end up not being included in the consensus history after all. But, of course, the more confirmations you wait for, the longer it takes before transactions can be considered finalized and before you could release external resources accepted in exchange for the currency. Third try, consensus-wise, proof of stake. Proof of stake utilizes a different scarce resource than either proof of authority or proof of work. Instead, it exploits the fact that we have both a consensus algorithm and a state machine, and it ties some in-protocol unit, which necessarily needs to be unit of value, some in-protocol unit in the state machine to the voting power in consensus. So validators in a proof-of-stake blockchain control some amount of this resource. They own, own a currency, some amount of the voting power, and they can utilize this voting power by signing, the same way as they would sign, sign transactions, by signing votes on a particular history. So often this proof-of-stake utilizes consensus mechanisms similar to BFT consensus, and it also often uses consensus mechanisms similar to a Nakamoto consensus, where consensus mechanism refers to the fork trust rule. So you can either have proof-of-stake distributed ledger in which validators send around votes to each other, or you can have one in which they commit votes to a particular chain, like proof-of-work miners commit work to a particular chain. But in either case, the unit of scarcity is this in-protocol unit, often a currency. The primary problem with proof-of-stake is that signing is not quite a scarce resource. Of course, if you don't punish signers for any kind of malevolent behavior, they can simply sign different histories without penalty. Just like in proof of authority, you have a different identity mechanism, a different mechanism of scarcity, but there's nothing preventing the validators from signing many different histories. And like in proof of authority, if the network is synchronous, this is safe, because you can simply reject any new histories, but if the network is even slightly asynchronous, which is always true in practice, you have no way to know which history is canonical, and it is extremely difficult to safely prove to an outside observer that the history that you're telling them and providing signatures for is in fact the one upon which the network has come to consensus. Luckily, we have control over the state machine. We can utilize in our state machine information about the consensus to try and make these signatures a scarce resource. We do this by identifying and punishing validators which are behaving against protocol, which are signing multiple different histories with the same stake. Signing multiple histories is fault attributable. It certainly has to be identifiable, since we must verify that a validator signed a particular history. We can use the same identification to notice when the same validator signs two different histories, and we can punish them. In order to punish them, we must have some in-protocol resource, under the name of the validator, the identity of the validator, which we can slash or we can remove, such that if they commit a protocol fault, if they double sign, or even do something else which is against protocol, maybe run an invalid transaction in the state machine, or fail to participate in consensus for a long period of time, then they will sacrifice some of this resource. The state machine will slash them, will remove some of the resource as soon as it detects this misbehavior. Now, with some caveats, we have made signing a scarce resource under the rational actor assumption. So if we assume that these validators are intending to maximize, and we must pay them in both proof of work and proof of stake, we must pay for network security via inflation, we can make it the case that these validators, if they are rational actors, will behave in accordance to the protocol. Or such is the hope of proof of stake design philosophy.